In this video, we will present a flexible two-stage trajectory planning algorithm that effectively utilizes environmental complexity information, designed for extreme scenarios. To address the challenges of poor generalization, inaccurate modeling, and inefficient planning often encountered by existing methods in unstructured, extreme scenarios, our method proposes a two-stage trajectory planning framework, where environmental assessment acquires environment perception and ego-vehicle states, evaluates task-specific environmental complexity, and seamlessly integrates it into both the front-end search and the back-end optimization. We use the classic 2D bicycle kinematic model for both search and optimization. In the front-end search, the environmental complexity determines the search direction, and a course trajectory is generated. In the back-end phase, we use the course trajectory as the initial solution and construct safety corridors around it to simplify complex obstacle avoidance constraints. Additionally, we evaluate the environmental complexity along the trajectory using the size of the safety corridors, which guides the adaptive sampling time. Finally, we solve the problem to get the final planned trajectory, which is executed by the downstream decoupled lateral LQR and longitudinal PID controllers. Following our previous environment assessment strategy, we define scenario-related metrics based on the surroundings near the start and end points, ego-vehicle parameters, and task distance. Combined with ISO 20900 standards, we derive the formula shown on the right. Scenarios satisfying this condition are identified as extreme. These are some of the results demonstrating extensive testing of our algorithm in open space, urban space, and randomly generated extreme scenarios. As illustrated, our method is capable of generating an optimal trajectory across diverse extreme scenarios. Subsequently, we performed additional Carla simulations employing a decoupled LQR and PID approach for lateral and longitudinal control to accurately track the planning trajectory. Building on this foundation, we deployed a sensor suite within the Carla simulator to collect extensive scene data, establishing a robust dataset for future end-to-end solutions. The configuration primarily consists of 4 surround view cameras and the bird's eye view. Subsequently, we validate the effectiveness of our algorithm on the real autonomous vehicle. On the left is the real scenario, while on the right is the monitoring of perception, planning, and control results. In the right panel, we present detailed lateral and longitudinal control information during trajectory tracking. The upper section shows lateral control, including the actual trajectory, and the curvature of the current trajectory corresponds to the fitted circular arc. The lower section displays the longitudinal speed control chart. The trajectory generated by our algorithm also demonstrates robust tracking control to reach the target point. The vehicle achieves global positioning using a combination of GPS and IMU, while employing a 16-line LiDAR to perceive and map surrounding obstacles and environmental information. Building upon this foundation, we implement our algorithm for rolling closed-loop trajectory planning. The planned trajectory from our algorithm is tracked at a control frequency of 100 Hz using a decoupled approach, where longitudinal control is managed by a PID controller and lateral control by an LQR controller. Thanks for watching.